Most of us know intuitively that in a head-on collision between a large dump truck and a subcompact car, you are better off being in the truck than in the car. Why is this? Many people imagine that the collision force exerted on the car is much greater than that experienced by the truck. To substantiate this view, they point out that the car is crushed, whereas the truck is only dented. This idea of unequal forces is, of course, fake. Newton's third law tells us that both objects experience forces of the same magnitude. The truck suffers less damage because it is made of stronger metal. But what about the two drivers? Do they experience the same forces? To answer this question, suppose that each vehicle is initially moving at 8 meters per second, and that they undergo a perfectly inelastic head-on collision. Each driver has mass of 80 kilograms. Including the drivers, the total vehicle masses are 800 kilograms for the car and 4,000 kilograms for the truck. If the collision time is 0.12 seconds, what force does the seatbelt exert on each driver? This is Chapter 9, number 22. We're going to start by writing out a diagram explaining what's happening in this problem. We have the truck over here moving at 8 meters per second with a mass of 4,000 kilograms. We have the car here with the driver also 80 kilograms, and the car weighs 800 kilograms. Because the car is moving in the opposite direction, we're going to give car having a negative velocity. We know the delta t is 0.12 seconds, and it wants us to find the impulse of the car and truck drivers. We know it's an inelastic collision, so we're going to use the formula m1v1 plus m2v2 is equal to m1 plus m2 times v final. We substitute in some numbers using the mass of the truck as m1 and the mass of the car as m2. And since the car is moving in the opposite direction, we give the car the negative velocity. We solve out for v final, and we get 5.33 meters per second. Next, we find the impulse of the truck driver. We know the formula for impulse is momentum final minus momentum initial. We substitute this for mv final minus mv initial, and then move the delta t over. We plug in numbers, and we get 80 times 5.33, which is velocity final that we solved for above, minus 80 times 8, which is the initial velocity, 80 being the mass of the truck driver, all over 0.12, which is the given time frame. We solve this out to 1780 newtons. For the impulse of the car driver, we use the same method, but we know that the car driver has to have the negative velocity, so it's going to be a much larger number because it's a negative times a negative. We use the same method and we solve it out to 8,886.7 newtons, a much larger number. And that's how you solve Chapter 9, number 22.